How we doing, folks? What's going on? You guys are spreading out like a gas. It's really interesting. I demanded that you all sit up front at the beginning of the class, and I've lost my aggression about this, but interesting. Yeah, interesting. Yeah, well, these things we call gas giants, not gas again. Nobody thinks they're made out of gas. In the sense that they're droplets that form in the same way as stars, that process potentially could happen extremely fast. And it's hard to say, working off the back of a gaseous model of star formation, you need some pretty extraordinary circumstances to get a ton of gas to kind of stick together like a star. There's serious thermodynamic processes with making that happen. So, for a long time, people have been trying to tell the story of gravitational collapse of these things. That didn't really work out because most of these clouds aren't actually gravitationally bound. They're kind of just expanding endlessly. So they introduced the idea of shock waves maybe to do it. But if you have a liquid star, it's actually quite easy to do because you just get condensation in cold environments, period. And so you can form these droplet type things rather quickly, and they can stick together with other droplets through basic electrostatic mechanisms that aren't exotic or weird at all. So yeah, you could imagine making a star or a planet pretty quickly in that sense. It's kind of weird to think of 300 million years as being quick, but compared to even the estimated age of our planet, right? It's like 4.5 billion, right? A billion's 1,000 million, so 4,500 million years old. That's a long time. So that's a really fast planet. It is far out and interesting, yeah. In some sense, it might make sense that from an evolutionary perspective, that the planets, the giant planets, like the gas giants, the ice giants, that they would be faster because they're closer to stars in composition. And if we think the stars can form really fast, then sure. If you want to do like this metamorphic idea that I dropped last time about these rocky things being formed at the heart of, say, ice giants like Neptune or giants like Jupiter, that might take a longer time because you got to blow all the atmosphere away and everything. There's another way maybe to make rocky planets too that I'll bring up today that might be a little faster that I've only recently become acquainted with. So we'll talk about that a little bit as well. But in general, you need some sort of a really immense pressurized system to make something really dense. Remember, the Earth is 5 times denser than the sun on average. So how in the world do you do that? It's a real, it's an expert level quest of a question for astronomy and astrophysics. One that doesn't totally have a satisfying answer right now in the textbook sense. So it's definitely a place we should expect to see a lot of progress in the future. Cool. What else? Any other thoughts? I forgot to tell this little story last time. I think it's worth mentioning. So, under the hypothesis that perhaps rocky planets are formed at the center of much bigger planets, right? They just lose their atmosphere through catastrophes or through, orbital changes. They end up next to the star and it evaporates their surfaces. A while back, we met up with this astronaut named Don Petit, who actually did his PhD here in Oregon, I believe at Oregon State. Could have been University of Oregon. I'm going to feel bad if I messed that up. Sorry, Don. I think he's on the space station right now, so he probably won't mind. But he had this cool theory with his advisor that stemmed from studying these really weird bird-like creatures that were around during the dinosaurs. They're called Quetzalcoatli. And they're not, they're technically not dinosaurs, but they may as well be. They're these big bird-like creatures. And they were studying these creatures because what was weird about them was that the wing of these animals didn't appear to be large enough to sustain flight. So, you can very easily look at everything from an airplane to a sparrow, and you can look at how big it is, how much it weighs, versus how big its wings are and the amount of lift that it generates. And you can plot basically this mass versus wing size on a nice diagram on a line. And everything fits on that line really nicely, except for these weird beasts from the dinosaur era. And so their question was, how in the world, well, first of all, did these things fly? And if they did fly, how did they do that? If they didn't fly, why in the world do they have wings? Pretty big wings, too. They seem to be animals that, it's hard to imagine developing a big wing if you're not using it for something. So they come down on the side of, well, they probably did fly because they have wings. And they try to talk themselves out of it, like, well, maybe they just jumped off of cliffs and did like the flying squirrel thing or something. But it turns out that doesn't work either. They couldn't even really glide much on these tiny wings. So they reason their way to the idea that actually, if the atmospheric pressure was something like 3 times what it is today, in other words, same ratios, still 80% nitrogen, 20% oxygen, everything's basically the same ratios of atoms, but there's just more of them per unit space. That if that were the case, the dinosaurs could actually have that buoyancy, right? Just like when you float in the ocean, right? You have some upward pressure because the water is really dense under you. It excludes you from it by density alone. That if the atmosphere was only 3 times thicker, then these dinosaurs could have flown, essentially, which is really crazy. And then they start thinking about it, and they're like, you know what? There would be no way to look into the fossil record and actually tell if there were pressure differences. You could see if there was more oxygen or if there was more nitrogen or something like that. You'd be able to see that. There's going to be chemical traces of that. But in terms of the actual overall pressures of the atmosphere at the time, they're like, there'd be no record of it. There's no way to actually tell. And so their conclusion is actually in line with, a number of other pieces of evidence that perhaps there actually was a moment in the past when this atmospheric pressure was much, much higher than it is today. Perhaps, as recently as the dinosaurs. And it's interesting because the more you go down that rabbit hole with the dinosaurs, the more things start to make a lot more sense about dinosaurs. I don't know if you guys have ever watched Jurassic Park or something like that, and you see these huge lumbering beasts, and you think man, how does that thing even walk without breaking its own legs? Right? It's actually a good question, and there's been some folks who have tried to do the math on the cross-sectional pressures that would be applied to the animal's legs. Their ability to pump blood to their heart under these conditions, stuff like this, where they just come up a little bit empty-handed, and they're like, I don't see how it's possible, actually. And the cool thing is that if, in fact, the Earth did have a much bigger, let's say thicker atmosphere, not even that much thicker, but a little bit thicker in the past, that it would solve all those problems for us, actually, in terms of the actual biophysics of how these animals were, able to essentially exist. And a lot of their body plans start to make a lot more sense as well, in terms of these big tails that they're kind of pushing themselves through this very viscous atmosphere with, and so forth. So anyways, that's a cool little piece, a little piece of the puzzle, maybe, as to the way the Earth might have looked differently in the past. And perhaps it has something in line with this metamorphic idea, this evolutionary idea of the planets. Perhaps, the reason we don't have any of those intermediate mini Neptunes or super Earths is because we used to be one, essentially. That obviously would have taken a long time for us to lose that atmosphere. Or maybe it just takes some sort of cataclysm. Maybe getting hit by an asteroid that's the size of Manhattan or whatever would do it. Maybe orbits change. It's not without possibility. There's this one period also in Earth's history, according to the geologists, where the whole Earth was covered in glaciers that were 5 miles thick, right? They call this snowball Earth, and it only happened once, from what they can tell, right after the appearance of life on Earth, and nobody really knows what that was all about. Could it have been a moment, though, where our orbit shifted and we weren't in a nice, cozy, warm spot in the solar system? I mean, maybe. Seems kind of interesting. So I think we're very much allergic as a culture to the idea that there's these cataclysmic changes that happen in our solar system. It's a very uncomfortable thought. And maybe we lean into scientific theories that make us feel a little bit safer at the end of the day. So, I don't know. What do you guys think? Anything? Yeah.
Maybe it was like a chemical shift in our atmosphere that caused the freezing.
That's an interesting idea too. Yeah, there's a lot of chemistry in the atmosphere. You would think there'd be, I don't know enough about it, but you would think that there'd be some chemicals that are easier to trace than, let's say, pressures or something like that. But yeah, people don't know. They really don't know. But it was so long ago, right? This is, I think, right before the Cambrian explosion, I want to say. It was a long time ago, billions of years ago. So it's hard to uncover what happened back then. There's so little rock available from that time period even. It's so hard to see. The surface of the Earth is constantly being remodeled. There's, tectonics and erosion and everything in between, glaciations. It's basically a new Earth all the time. We've been constantly pummeled by asteroids, but you don't even see that many craters from them these days because the Earth kind of heals itself so easily. Any other thoughts about that?
There's a big asteroid coming towards us.
There is. I did see that. Yeah. Yeah, it's not good. I don't know. I mean, I think that the percent chance of it hitting us is pretty low. Super low.
It went from 1% to 2%.
2? That's not good.
They went from that to that.
Yeah. Doesn't it? It's not supposed to arrive for like a decade. Yeah. Well, I think a decade should be long enough for us to. Last semester I spent a whole lecture going through all of the different ways that we might deflect asteroids, and there's a lot of plans about how to.
Too late to deflect this one. So yeah, like if we wanted to, like we missed that window.
No.
Yeah. So like the fact that it just went up like that, it's like, but it's not like world ending, but it's like.
It would hurt.
Wiping out.
Yeah.
Wipe out like New York.
Interesting. I mean, there is a huge. There's a couple of things here. So like asteroids, they usually don't just like come straight down from the sky and smash into the Earth. They usually kind of glance off the Earth. That can be really destructive. Yeah, they explode right in the atmosphere. And so these are called bolides when they do this. And there's been some pretty gnarly ones, even in the last, even in modern history, let's say. So there was a huge one in Russia over Siberia back in 1910 that wiped out a huge section that would have, if it had been over Paris or Manhattan or something, it would have been lights out for sure. But the good news is, even 2% chance this thing hits us. I don't know what angle they're projecting it would hit us at. Probably not dead on. But the good news is, it turns out humans mostly live in tiny little pieces of the Earth, right? Like way more than most of it is water, first of all. And then on top of that, if you just look at the land, people are concentrated into the tiny, I don't want to just drop numbers without knowing them, but most people live close to bodies of water, the ocean or lakes, and most people live in cities. So now you're really narrowing down the set of possibilities of where this thing's going to hit. The likelihood of it striking Manhattan or Portland or something is astronomically low, even if it's 100% going to hit the Earth. So, should be cool. Yeah. It's not a joke. There's reason to be concerned. Now, also from the optimistic standpoint about that, I think it was not until about the late 1990s that NASA even decided to start tracking these things. So there was this comet that actually broke up and slammed into Jupiter in 1994. And they got these beautiful pictures of it with the Hubble Space Telescope. And I think that was the first time that those images made their way to Congress, and there was congressional hearings, and people were like, hey, this could be really bad. There was this huge comet fragment striking Jupiter with, I think the same force as the one that ended the dinosaurs and stuff. Now, Jupiter is a huge planet, so it kind of grabs up comets. It's actually perhaps part of the reason why we're still here. that we have a huge giant planet that'll scavenge things like that. But yeah, over the course of, I don't know, 20 years or so that they started tracking these near-Earth asteroids, I think they've accounted for, way more than 90% of the ones that are dinosaur ending.
Because they like actually have teams that like hit these asteroids to like deviate.
They've tried it on at least one or two. Yeah. 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 Yeah, they did. They tried that out. I think was it called Deep Impact, that one? I can't remember. What's cool is they actually sent 2 spacecrafts. One of them like smashed into it, and one of them was like the follower who took the sort of the camera shot. But yeah, it turns out you basically only need to hit these things a little bit because they're on a trajectory, right? So you just kind of push them off. You can also just put a little orbiter around them, so that you basically make a little moon out of your spacecraft, so it orbits it, and that can kind of wiggle the thing off. So there's all sorts of proposals of how to do it. I think that I like to think that we have gotten technologically to the point that we'd probably be able to figure something out. 10 years out that's good that we're seeing these things 10 years out. That somebody's job is to figure this out somewhere. This is very interesting. Yeah, 11. Oh, yeah? Interesting. I mean, there might be different ones from time to time. And then I think occasionally they get deflected by other means, It's very, very difficult to calculate the orbits of multiple bodies in the solar system, right? So you can do this nice Newton law that we talked about to calculate how 2 bodies are going to orbit each other. 3 starts to get into I think it's 9 differential equations that govern the behavior of them, and there's no generalizable solution. 4, 5, 6 bodies, you're getting into computational spaces that are really, really complex. And so I think it's really hard to actually say for certain what's going to happen with any of these. But there's probably alarms that get triggered, things that are more likely than others to be a problem. So I don't know. I'm an optimist. I think we'll be all right. But I think it's been a problem for people in the past, for sure. I think that we probably have suffered some pretty gnarly impacts in the past. There was a huge volcano that went off just I think it was only 70,000 years ago. The human population dwindled down to a number of thousands of people or something like this. Kind of crazy. So we've definitely been through some stuff in the past, and probably have to go through something in the future.
Seems to be.
Yeah, I mean, it's what would you say? We're in the crosshairs of a lot of different moving pieces out there in space, for sure. And that's not even bringing in solar flares and stuff like that, which could be pretty gnarly as well, at least on our technological civilization. So, thank God people are studying this stuff. All right. Let's talk about the ends of stars. Michael, would you say the deconstruction of stars? I like that. So much of our job as astronomers, as students of astronomy, is to make sense of this basic diagram, right? I mean, we introduced this in the first week of the class. This thing, the HR diagram, kind of summarizes everything that's obvious about stars, right? How bright they are, corrected for distance to the best of our ability, versus how hot they are to the best of our estimation, assuming that black body temperatures are perfectly on point for their temperature. And then we try to tell the story off this thing, And so last time we talked a little bit about how stars, kind of glom together and end up on this main sequence, right? And that story seems to be, in some sense, it's regardless of your understanding of stars, you kind of end up telling the same story about that, right? So this entire course, we've been juxtaposing the liquid model of stars versus the gaseous model of stars. And in terms of the creation story of stars, the construction, as Michael put it, you basically end up with a similar story, depending liquid or gas. The point is, at some point, the stars have enough material to start fusing, and they find themselves on the main strip, the main sequence of the HR diagram, right? So the stories start to diverge pretty heavily at this point when we start thinking about how stars leave the main sequence. So, I'm just going to review this for you guys real quick. So stars, under the gaseous model, stars are mostly made out of hydrogen and helium. Bigger stars perhaps have bigger stuff inside of them that's fusing. We'll talk about that in a minute. They're born out of this shock compression or gravitational collapse of some sort. Chemistry is starting to be investigated under the gaseous model, but it's not entirely there yet. The stars make the biggest elements they can. So if you have huge stars, you can make bigger elements. The giants and the pulsating stars have to do with this destructive end of the stars. And we're going to talk about that standard model today a bit with why these red giants are expanding in the first place, what's going on. But the gaseous story is something like different types of fusion start happening in these at the end of their life. As their fuel runs out inside, they start collapsing on themselves and doing new types of fusion. And this is quite destructive and ultimately results in them blowing themselves apart. With the liquid model, liquids are weird because liquids are, by definition, incompressible. So you don't get any of this weird collapsing stuff at all. That means the stories that we tell downstream of it follow a very different route. And we end up explaining the differences in the appearance, so why they end up at different places on this diagram in the dwarf space and the giant space, largely based on restructuring of the lattice and the changing of the optical properties of the hydrogen and their surface. We also, with the liquid model of the stars, don't necessarily need everything to be happening deep inside the core, because we don't need enormous temperatures in order to fuse elements all of a sudden. So stars could be fusing elements in between the layers of their liquid metallic hydrogen. And we're going to juxtapose that today a little bit more. And so we basically are entering this point where our projection of what happens at the end of the stellar cycle is going to diverge really greatly. And I want to make sure to give equal opportunity, I like that, equal opportunity to each one of these theories as we walk through it today. For those of you who've been reading the textbook, you've probably gotten a good dose of the gaseous model. But even if you haven't, everything that you love as a science fiction reader, black holes, white dwarfs, pulsars, neutron stars, these are all consequences of a gaseous collapse model. We don't get any of those under a liquid model. We just get things whose optical properties change. So it's far less exciting, but there's something compelling about it nonetheless. Particularly because of the fusion story. If you guys are interested in cheap, abundant, clean energy, figuring out fusion probably matters a lot. So let's dig into it a little bit. On the gaseous main sequence, the lifetime, how long something is going to take to cook through it, really depends largely on how hot it gets. In other words, how much stuff there is. The bigger it is, the more compression that happens, the quicker that it burns through that fuel at the core, right? So the gaseous model of stars is all about fusion reactions that are happening at the core. The more mass you have, the more pressure, the faster you cook through all of that stuff at the core. And so the stars are thought to live for a very short amount of time if they're too big. And this is summarized in your textbook with this figure. Now, the story might be a bit more mundane with a liquid star. With a liquid star, as opposed to having like these planets burn through their fuel and explode or turn into red giants and then turn into dwarfs, you might actually imagine the stars just sort of cooling off naturally down the main sequence. So they would just kind of flow down the main sequence gradually as they cooled off naturally just due to thermodynamic entropy, essentially. So it's a far less fantastical story. So we get into some new and interesting fusion reactions under the gaseous model as these stars start to age. So our first job, by the way, is going to be explaining these giant stars. So the story goes for the gaseous stars that as they exhaust their fuel in their cores, and this is proposed to happen to our sun one day as well, it will eventually use up all of that nice fusible hydrogen and helium, and it's going to start to collapse at the core, and new heats and new temperatures will be generated so that that helium can start to fuse at that point. And as it does this, there's these expansive processes that essentially lead the star to blow up like a balloon, at which point it moves off the main sequence into the giant and supergiant phase over here. So that's what we're working towards. So as that core starts to shrink, all of that infalling material is converted to more heat, which drives up the temperature and gives us the opportunity to have additional reactions that we wouldn't expect otherwise. Now, what is apparent is that there are some enormous red stars out there. That portion of the HR diagram in the upper right does seem to be apparent. There are certainly stars that are very luminous, and they're pretty cool. They're red, right? They're not glowing blue like you might expect for a star that is happily going through its life cycle. Something has changed that's interesting. This is a kind of a comparison. There's the Xi Cygni, which is a supergiant, and Delta Bootis, which is a pretty reasonable giant star compared to our sun. And the thought is actually, according to the gaseous model, that as our sun starts to die some several billions of years from now, that it will evolve into something like this over here, upon which it will go through some catastrophic death process that we'll get to in just a second. So the basic idea here under the gaseous model is that as it expands like this, you actually get a cooling as it happens. Sometimes this can lead to pulsations, right? So you guys probably noticed this. If you take like the lid off a pot of boiling water, the steam actually cools down. It cools down the pot as it expands, right? So this expansive thing, it's actually called adiabatic mass loss. But as you cool down something that's expanding, as something expands and loses that material, it cools down a little bit. So you have this cyclic kind of pulsating thing where that core is getting hotter, it's pushing mass off of it, it's losing layers, and as it does that, it actually cools and collapses back down. So you get kind of these pulsating mechanisms. There's actually one of these theorized to be occurring inside of that constellation Orion right now, right? So we've talked a little bit about Betelgeuse, right? You should be able to see it if you go out at night. It's actually pulsating on the order of days. So you can actually see this thing brighter some days than other. And the thought is that it's going through this kind of red giant transition. Eventually, it's thought that, I believe that it's estimated to be sometime in the next, I want to say very soon. I know very soon for astronomy is like 100,000 years, but sometime it's expected to completely shed all of its layers and go through this process of novaing, or this final expulsion of its outer layers, upon which just the little core will be left behind. So, to summarize that, basically, all these stars are expected to, any star, as it goes through and uses up all of its core hydrogen, it's going to start to drift off the main sequence. So, this is an interesting on several levels. Because there's a very small pocket of giant stars, actually. If we go back to that, let me go back to that slide. Most of the stars we see fit really nicely on the main sequence. Very few of them are in the giants pocket, and even fewer of them are in the white dwarfs. But according to the gaseous model of the stars, all of them should eventually leave the main sequence, go through this giant phase, and then some of them will either create these compact objects called white dwarfs, or even more compact objects called black holes that we'll deal with, I think, next week. Of course, according to a liquid model of stars, liquids are incompressible. The stars actually just cool off naturally after they're formed through these condensation reactions as they're losing mass. Obviously, our star is just spraying hydrogen into interstellar space. That's what the solar wind is. Sometimes there's these coronal mass ejections. Basically, the stars are just shedding their material all day long. And eventually, this results, it's a cooling process, and the things just kind of drift down the main sequence. A lot less exciting. There's also a model for what's going on with the giant stars under the liquid model of the stars. This is kind of interesting, actually. So one of the things about the liquid model that's really different from the gaseous model is that in the liquid model, fusion doesn't have to occur only at the center of the star. So in these giant fusion chambers where the scientists are trying to make fusion power for us here on Earth, what they have to do is they have to raise this gas to millions of degrees in order to have the kind of energies necessary to smash these atoms into each other and have them stick and make a new atom. And they try to confine them with these really powerful magnets, right? In the lattice-confined fusion experiment, you actually can do it at room temperature. It's not that big of a deal. You essentially impregnate a material with the substrate that you want to fuse, the atoms you want to stick together, and then you let the layers, the actual whole body, the structure of all the bonds that hold that lattice together, it does the confining work of the analogous magnets in the gaseous model. And you actually just kind of squish it a little bit from the outside, and these atoms will fuse together. So inside of the liquid model, it's all about these intercalation zones. Anybody ever heard that word before, intercalation? That's a good one to bore your roommates with later. Intercalate. It literally just means to have one material get sopped up into another material. So have you guys ever used masks with carbon filters? Or maybe you have these HEPA, I don't know if HEPA filters do it, just carbon filters in general. You guys seen carbon filters on, they're usually on these respirator masks is a good example. That's the only one I can think of right now. This is doing the exact same thing. The carbon lattice is actually absorbing into it little impurities that you're trying to get rid of, whether it's poisons from some painting project you're doing or whatever. They're getting intercalated into the lattice of the carbon in the filter. So this is something which is really interesting, and it's been studied greatly in graphene. Do you guys know what graphene is? Anybody ever heard of graphene? Graphene's kind of an interesting 21st century mega material, right? It has superconducting abilities. It's very lightweight. It can be very strong for construction projects. But essentially, graphene is interesting because it has the same hexagonal lattice to it, which is proposed for liquid metallic hydrogen, which is at the core of the liquid, which is at the center of the liquid star model. So it has a very similar lattice structure. And there's been a number of really interesting studies done about how materials intercalate into the layers of graphene. And one of the things that was noted when they were studying graphene intercalation of materials was that if you got a graphene material, which is also layered in this very kind of onion shell-like manner, if you get materials to be absorbed into it, and then you apply some external pressure, whether it's like heating them up or whether it's even just shocking the system, there's a small chance that what will happen is that those molecules that have been absorbed, let's say it's a nitrogen or something that was absorbed as a gas and then became embedded into the crystal of the structure, so it's part of a solid, that it will revert to that gaseous form. When it does that, it basically makes something of a violent explosion, actually, or what appears to be these little blistering bubbles on the surface of the graphene. And it sheds individual layers of that onion skin off of the graphene. So all of this is to say that in a liquid model of the sun, you have every opportunity for these expansive processes where materials can go from liquid to gas and essentially sublimate and create these pockets where the actual surface of the star is expanding, perhaps even violently in the case of a supernova, something like that. So again, very different process under the liquid model. The fusion elements don't necessarily need to be happening deep inside of the star. Whereas in the gaseous model, all of our processes have to happen in the core of the star because that's the only place with 15 million Kelvin temperatures that are capable of fusing gaseous plasma. Interesting stuff. Questions about that? I know that was very technical. I apologize, but it has to be done. It has to be done. You good? All right. So, all right. Back to the gaseous model. Actually, either way, stars certainly do leave the main sequence from time to time under either model. In the gaseous model of stars, they have to leave the main sequence. That's the only way that a star can evolve, is eventually it's chewed up all of its fuel, and it leaves the main sequence as a red giant. So it drifts off that sequence. And this, of course, is what we're seeing in Betelgeuse. Either way, something as interesting is happening because we have a pulsating star that is visible with the naked eye. You all should check it out. But under the main sequence, under the gaseous model of the stars, we can actually figure out something approximating the age of these things. The mass of these will tell us exactly where it's going to peel off of the track. So let me see if I can interpret this for you. So the basic takeaway from this one is the more massive the star is, the more quickly it's going to peel off that line and find itself in the giant phase, which makes sense because, again, more massive, more pressure, more temperature, the faster it's going to get to the end of its life and find its way off of the main sequence. So let's see where I want to go with this from here. I was going to talk to you guys a little bit about star clusters, but it seems out of place right now, so I'm going to skip over this. And all right, I want to talk a bit about the actual fusion mechanisms a bit more. All right, so let's examine the end stage of these gaseous stars. So one thing that's kind of interesting, in the gaseous model, the star's the size of our sun. And remember, our star is pretty big, honestly. It's bigger than maybe 90% of the stars. But it's pretty garden variety in terms of there's a lot of stars that are about the same size as us. But our star is only able, under the gaseous model, to fuse hydrogen and some helium, right? And we'll talk about that helium in a second. So the question becomes, how do you get these other elements out of it? So part of that has to do with whether you're a big star or not. But there's some kind of interesting processes that happen in theory under this gaseous collapse that's going on during this red giant transition. And I want to talk about those for a second. So like we said, these red giants have basically turned their cores from hydrogen into helium. And there's no energy generation taking place inside of these. So what's happening under these models is that the gravity starts to crunch down on the interior of these because remember, under the gaseous model, the only reason the star doesn't completely collapse is because there's this outward pressure from the gas that's pushing outward. Now there's issues with that, but I'm not going to pick on them right this second. But needless to say, as soon as there's no fusion happening in the core, it's just all turned into this helium that's kind of inert, the whole thing starts to crunch down on itself. So the story goes that as it crunches down, it gets really, really hot. Once it reaches some stupefying temperature, like 100 million Kelvin, which is just mind-bogglingly hot, it starts to actually undergo fusion between those heliums. And the heliums can actually fuse together and give us carbons. So, we're starting to actually move up the periodic. I can't actually pull this back. Yeah, so, yeah, maybe it's worth doing, actually. So, our real goal here is to figure out, all of these atoms are arranged in terms of their size, essentially. The only way to make these really heavy things is to smash the smaller ones together and to do fusion on them. So far, we've been talking about that tiny little atom up at the top left, right? And this thing essentially reads like a book, right? From left to right across the rows in terms of the weight. So I wish I could turn off the projector for a second while I do this. anyways, so the idea is that at this point, the temperatures are hot enough that we can at least start to squish these heliums together in a way that allows us to get carbons to appear. So this process is called the triple alpha process. And it creates a sort of feedback loop where you have extra energy that's generated because now you've actually flashed the core. The helium core has had this revitalization where it's able to do all of this fusion all of a sudden. You have new heat generated. You have that heat starts to contaminate the outer side of the core. This is kind of loud. Hold on. All right, so the idea, whoa, that came down really, goodness gracious. And the basic idea is that it can go through this loop several times, right? So, all right, it can actually it can go through, it can flash its helium core like this, right? It's compressing and compressing, flashes, ignites it, creates some carbon in the process. And then it uses up all of that, but then there's extra helium in the outer layers around it. Those can flash as well, and you basically get this feedback loop where you can keep cycling this process for a while. This is kind of thought to be the main part of the red giant's lifetime. So the result is, if you look at something on the HR diagram, that what's essentially happening is that the star's drifting off the main sequence, right? Because, well, it's getting very big, and it's cool, right? It's red, it's not blue. It's drifting up there to the upper right. And then it has this helium flash. Okay, it starts to get a little bit hotter. It starts to get, it starts to perhaps come back down to a reasonable size and radius. And it can actually go through this loop several times, right? And so, great. We have a way that a star, a reasonable sized star such as our own, could eventually come to the point where it's able to make carbon, oxygen, helium, obviously, plenty of helium. We have a situation where we can get some heavier elements for the first time. Eventually, this whole thing is going to run through all of its fuel, and it's going to keep collapsing on itself. The key concept here with this entire gaseous story is that these objects continue to collapse on themselves and continue to collapse on themselves. Again, that's only possible in a gas using ideal gas law equations, right? You can always take a gas and compress a gas and compress a gas and compress a gas. In reality, when you compress gases down to a certain point, what happens? They turn into liquids, yeah. Liquids, the reason, you guys ever seen like hydraulic systems, like hydraulic lifts? Anybody ever used those before? You can see them on airplanes, right, where they move the flaps of these hydraulics. The essential idea is that you can squeeze the liquid at one end of a big, long piston type thing, and you can do incredible work with it at quite a distance away from where your actual actuator is located, because the liquid just shifts the force almost instantaneously to the other end of the process, right? It's really, really useful. So you end up with a system that's always kind of falling in on itself. All of the work is being done by this collapse. And so the end result is that you have these stars that are crushing themselves and crushing themselves and crushing themselves to death. Now, the idea is, as it's kind of crushing down like this, it's also going through this cooling stage at the surface, right? So these outer layers are being constantly shed. And this seems to be the case really in either the liquid or the gas model. The outer layers are certainly being shed. We have millions, not millions, we have maybe thousands of examples of these. What we call them actually planetary nebula, which is yet another incredibly bad name for a celestial object because they have nothing to do with planets. The people 300 years ago who discovered them thought maybe they were planetary systems, I guess. But basically the stars, at some point, we see actual layers of material just being completely shed from these stars. Now, what's really interesting is that in most of these cases, what's left in the remnant of this is a very non-luminous but bright white object, which is called a white dwarf. So this is kind of the last stage in the gaseous collapse of the object, which puts us basically at the point of having to deal with white dwarfs, and we'll get to those hopefully today. I'm a little bit behind in this course, so I would like to make it to the white dwarfs. Now, let's see. You know, massive stars that are bigger than our sun, they actually, under this gaseous model, they evolve very much the same way, except you have the opportunity to make a few more elements beyond carbon and oxygen. So let's look at that. The basic idea isn't too much different than what we've talked about before. It's just that because that collapsing weight is so much more in the case of these giant stars, we actually have the opportunity to fuse new elements. I'm not going to raise the board again, but you can move your way down the periodic table a little bit more. So you can start making heavy stuff like magnesium, neon, oxygen, oxygen fusion into stuff like silicon. The party stops at iron. Iron seems to be the biggest molecule that you could possibly fuse using the biggest stars collapsing on themselves as gaseous plasma. You can't really get past iron. Without raising this thing, iron doesn't get us maybe halfway down the periodic table. So then we have to actually talk about these violent explosions in terms of producing the rest of the elements that we're going to get into. One thing that I think is really interesting, actually my friend Jeffrey Walensky pointed this out to me, and I'm not even totally sure what it means, although I told you guys I would introduce another planet formation mechanism for you today. This thing here is really interesting. So this is the end stage right before this thing sheds its outer layers and becomes collapses finally into a white dwarf or a black hole under the gaseous suns. This actually looks a lot like a primordial Earth, if you think about it. It's got a huge iron core, it's got a bunch of silicons and sulfates, and basically everything else you'd need to make oceans and atmospheres out of it. Now, that's a really interesting coincidence. But what's fascinating is that under the liquid model of the stars, you have a lot of these elements being fused, especially in huge stars. You have them actually being fused in between the layers of the lattices continually. And so the proposal is on the table that one way to make really dense rocky planets would actually be similar to what I was describing to you guys with this kind of explosive decompression of the lattices in graphene and the expulsion of these chunks of material, that you would have the same sort of thing happening within the lattices of these liquid stars, where they would essentially be able to burp out things that looked a lot like gobs of, dense metal, similar to rocky planets, moons, different satellites, asteroids, things that are really, really dense. You have perhaps a mechanism by which to do that. And in either case, it's very, very interesting that the end stage, even in the gaseous model of heavy stars, happens to have a really similar composition to a planet itself. Now, the Russians I told you guys about a long time ago, particularly this biochemist named Oparin, he actually thought that stars cooled off down the main sequence and eventually just cooled off to the point that they looked like planets. Like, that's how you make an Earth, is you cool a star off. Right? So the Russians were kind of isolated during the Cold War. They didn't have any need to come to consensus with the West about how these things happen. So they had a very different story about how this might work out. I don't know if that's true. I don't know if any of those stories are true, but it is very tantalizing that what you have here is something that looks very much like a primordial Earth or a primordial rocky planet. Now, what we're going to talk about, what happens next, I'll probably get into this next class, is that when a huge star gets to this point, the next stage for it is a violent, violent explosion. And I'm not going to tell you all the details of that today, but what is interesting is you can imagine that in a violent explosion, you might end up littering with the interstellar space around you with lots of blobs of material that had a lot of these compositional elements to them. In other words, you might make some little planet seeds in the result of it. And I'll show you guys some pictures that actually make that case even more compelling, that there's these kind of giant blobs of iron and stuff that are found in the supernova remnants that we see. So anyways, another possible planet-making situation that helps us get to that density issue. You can go down the liquid road if you want. You can go down the gaseous road if you want, but perhaps there's a way to make super dense planets in that fashion. All right, questions at this point? All right, I'm going to skip this cluster stuff because I don't think it's as interesting as other things. All right, so I'm trying to catch up. I'm going to go forward into our next lecture a little bit. All right, so at that point in the story, when we're making these planetary nebulas, these stars are shedding their final outer layers. Now, the standard story that results is that under the gaseous model, all the stars go through this end phase of their existence, this deconstructionary phase. Pretty much everybody has to go through this journey off the main sequence. They have to go through these exhaustion of their fuel supplies and this violent shedding of layers, which results in the thing completely exfoliating. It's lost all of its layers, and it's just a tiny little kernel that's left over called a white dwarf. Okay, under the liquid model, something interesting happens to some subset of stars. They leave the main sequence because, for whatever reason, their lattices are unstable. They shed layers, and there's also a white dwarf that's left behind. It's not happening to all the stars in the liquid model. It happens to a subset of them. It's more of like an exceptional catastrophe than something that everybody has got to go through. In either case, we have to explain the white dwarf. What the heck is a white dwarf? White dwarfs are really, really weird. We've rubbed up against them a little bit in the past. But remember, white dwarfs are these weird guys on the HR diagram that appear to be really, really dim, but really, really hot. And that's an anomalous situation in terms of the story we're telling, right? Because generally speaking, if you're really, really hot, you should be really, really bright too. Because how do you get hot? You have a lot of atoms doing a lot of fusion, right? So white dwarfs are weird. The way that they fit into the liquid story and the way they fit into the gaseous story is very, very different. So the gaseous story tells us that now that this thing's completely exfoliated, it's burned all of its fuel up, it can't do fusion anymore, it's expelled all of its layers. There's just a bunch of heavy stuff sitting there. And this stuff is still in this plasmatic state, which is challenging to imagine, but it is. The core is still supposed to be in this plasmatic state, and it continues to just, now that there's no pressure, it's not doing any fusion, there's no push, no radiative pressure, it's not making light, it's not doing any fusion, it just starts to collapse on itself. And it collapses, and it collapses, and it collapses. And the end result of that is, depending on how much mass the star started out with, the thing will crunch down to it's going to have a lot of those heavy elements left in it, and it's going to just crunch down and crunch down. And at some point, depending on how many solar masses it is, its radius is actually going to go down to nothing. It's hard to say this with a straight face, but the theory literally projects that the thing, this gas ball of stuff at the center of these stars, is going to collapse down. If it's 1.4 times the size of our star, it's going to collapse down to zero radius. Okay. So, and that will take us into the story of black holes that we'll get into next week, I believe. Now, okay, what does that even mean for a ball of gas to crush down to the size of a grapefruit? Let's not even talk about it crushing down to zero radius. Let's just talk about what in the heck that would look like. The proposal is that it's a new form of matter that we've never seen on Earth, that it's this exotic goop of stuff that is essentially, by all metrics, the same as a metal. So we're talking about all of the electrons are delocalized from the atoms. Even the protons become delocalized. It's essentially just this soup of primordial particles of some sort. But it's got an incredible density, completely unfathomable. Now, under the liquid model, of course, we have to answer this question a little bit differently because obviously liquids are incompressible, so that's not going to work for us for a liquid model. We're not going to be able to crush it down to 0 radius. What we can say is that the equation that we're using, sorry, not we, but the equation that's being used to give us the slope of this line and so forth, the equation that's being used to predict the right dwarf's radius also has this really interesting component, which is an epsilon, an E, in this diagram. And the epsilon is the emissivity of the material, right? So remember, the only difference between soot, graphite, graphene, soot, and diamond is the arrangements of the atoms. You put graphene under, or soot under a ton of pressure, and you can make diamonds. Now, diamonds have an emissivity of almost 0. Soot has an emissivity of 1. That means if we go back to this equation over here, everything works out just fine if the emissivity is 1. If it's 0, then all of a sudden your luminosity is going to go way down, actually. In other words, the thing is going to appear at whatever temperature it appears at, but it's going to be really dim all of a sudden, simply because the liquid lattice has changed in such a radical way. If the star is a gas, then emissivity is not a factor, because for gases, the emissivity is always approaching 1. So it's a complete non-issue for people who are dealing with a gaseous model. We have a very different situation when we're dealing with liquids. In other words, we can be starting to imagine a situation where the white dwarfs aren't these ultra-dense compact objects. They're actually just normal stars that have undergone some shift in the way that their lattices are organized, which perhaps makes sense because if you think about it, the stars under the liquid model and under the gaseous model, they've lost all their outer layers, right? They've lost the region of the star that was under the least amount of pressure. So they lost all of that stuff, basically. That means the stuff that was under the greatest pressure is that stuff. And that stuff, at least in carbon, which seems to have an identical lattice structure to liquid metallic hydrogen, is completely optically transparent. So you can see right through a diamond, right? Its emissivity is extremely low. It's very optically inactive, I think is one way to maybe think about it. So it would make sense, perhaps the core remnant that's left behind in a liquid star doesn't have a lot of optical activity. Perhaps we can just simply explain the white dwarf as a different optical remnant with a different lattice structure. So that's quite interesting. So you end up thinking about these things in terms of a phase diagram, where depending on the amounts of temperature and pressure, the lattice actually arranges in a different capacity, which gives you very different optical effects as a result of it. And you don't have to have these impossible, never seen before substances that occupy, the mass of the sun in the size of a baseball or something even smaller, perhaps, that we'll get into next week. So, two very different stories that you end up telling as a result of this story. Another case, what you have is stars which are traveling, in either case, from the red giant side of the main sequence down into the white dwarf side of the sequence. The question really then becomes, is this something that always happens to every star? Is this certainly going to happen to our star? Or is it something that's quite anomalous that has to do with, peculiar irregularities in the absorption of different pockets of material, or the way that the different fusion elements are burped out of the sun over its lifetime? It's really interesting. I learned one thing this morning that was quite fascinating, which is that, and this is kind of in favor of the idea that there might be more to this fusion model than simply happening at the core, which is that these coronal loops, these really beautiful, like explosive loops that you see at the surface of the sun in these NASA images, they have something like 10 times the amount of helium that they should have, actually, compared to, like, let's say, the background rate of helium in the star, which is an interesting line of evidence that perhaps that these fusion processes might be nearer to the surface than we had originally thought. And I think we're going to keep kind of uncovering little elements of this story that challenge our original understanding. For me, it's very, very, and I mean, as we move into next week and we move into black holes and so forth, we're going to get into a place where the science starts to border on science fiction a little bit. And I guess what I'm trying to offer you guys is that it's not necessarily the only way to solve these problems. Although it is a lot more fun. I will definitely admit that black holes are a ton of fun. I love me some science fiction movies about black holes. But you can't make a black hole with a liquid star. What do you think? What are your guys' thoughts? Give me some, we got 5 minutes left here at least. 11. Neutron stars are just white dwarfs that are even made out of even heavier starting materials. So they just crunch down and crunch down and crunch down even into an even more degenerate material, essentially. We'll talk about them a little bit more later, though, yeah.
On your last ending note about like how liquid stars can't make black holes, do we understand black holes enough to say that?
Oh, I promise you we will do black holes their justice, for sure. I will present many possibilities for what in the world could be going on with black holes. Aliens! That's one I'm not going to blame on it. Maybe Shabilsky's star gets the alien treatment. Yeah, Jasmine.
To even add on to that,
Mm-hmm.
is that like recently we're like, oh yeah, hey,
That black hole's actually a star. Like,
That's been happening a lot, too. So a lot of these black holes that were initially reported as black holes, say in the 90s and so forth, the more powerful telescopes we get, we say, oh, wait, there's actually a little white dwarf there, actually, after all, right? Which, yeah, we'll see. But every year, more of these black holes are getting converted into white dwarfs. Black holes are weird, guys. Like, we'll talk about them. Basically, what I like to say is anytime you see black or dark or anything like that in science ever, it usually means, like, we haven't figured this thing out yet. It's like kind of like a variable in an equation, like an x in an equation. It's like, I don't know. Like, that could be anything. It's usually referring to some anomalous process. Maybe something is orbiting, something we can't see. Stuff like that, where, the gravitational dynamics don't make sense. And so the easiest way to solve the problem is to stick something really heavy there that can't be seen. But there may be more simple ways to solve that problem, particularly if you start considering the optical qualities of real materials, not transparent gases, but you actually start thinking about the stars in a different manner, which I think is the real revolution that is unfolding underneath our feet in this classroom and in the world abroad. So it's really exciting time. My wife and I are putting together a conference this summer for a cosmology conference in Portugal. We're inviting some of the biggest critics of the Standard Model with some of the staunchest defenders of the Standard Model. And it's not going to be a fight. It's going to be a real discussion of what comes next, because even the Standard Model proponents kind of realize that a lot of this data coming in off these new telescopes doesn't make a lot of sense. And so everybody's very curious for what the next generation of astrophysical models is going to be. I think it's going to be an absolutely mind-bending year. I would not be surprised if you guys start seeing incredible headlines about all this stuff in the next, I don't want to jinx it, but soon. It's going to be pretty phenomenal. So anyways, I'll let you guys digest that. We'll talk more about it on Thursday. And have a great week, folks.